Thank you very much. It's a pleasure to be here. I want to thank the organizers for inviting me. It is indeed an honor to be here representing nuclear physics, and I am going to talk about how one can apply effective field theories to nuclei. So my lectures will connect to Professor Kaplan's lectures and also to Dr. Mohapatra's lectures next week, or later this week and next week. I want to begin with a couple of facts about myself. So I grew up, as you may soon detect, in Australia. And I went as a postdoc to the US. In fact, I was a postdoc in Seattle when Professor Kaplan and others were doing all the developments that he was talking about earlier this morning. And then I became a professor at Ohio University, which is the oldest university of higher education, the oldest institution of higher education west of the Appalachian Mountains, founded in 1804. And it is not, this is very important, it is not the Ohio State University where Dr. Mohapatra was a student. It's a different and older university in the state of Ohio. All right, so I discovered that I have two things in common with people here in Bengaluru. The first thing is that both where I grew up in Adelaide, South Australia, and Bengaluru are on a half time zone. This is a truly shocking thing to all Americans that half time zones exist, but obviously not shocking to you. Adelaide is at present 5 hours in front of Bengaluru, as any of you who watch the cricket and enjoy watching cricket from the beautiful Adelaide Oval will well know. And secondly, Australia and India share the same national day, January the 26th. But of course, in Australia, it merely marks the first day on which convicts landed in Australia. All right, so with that brief introduction, let me change gears and talk about nuclei. So let's do the following. So how many of you are PhD students? Okay, and how many of you are postdocs? Okay, and how many of you are like more senior faculty, staff at a lab, something like that? Okay, that's very helpful. Okay, so that helps me know sort of what level people are at. So regardless of which category you raised your hand under there, it's probably a little while since you thought about nuclei. All right, unless you happen to be doing a PhD in nuclear physics, but I was told that everybody here was a particle physicist. And so for you, you hear the word nuclei and you're like, oh, too complicated. All right, so let me remind you of some things that hopefully you learned as undergraduates about nuclei. So the first thing you probably know is that the binding energy per nucleon in a typical nucleus, well, actually, yeah, in all nuclei is less than about 8 MeV per nucleon. So every time you add another nucleon, you gain about 8 MeV of binding energy. This, of course, is the mass defect, right? It's not the total energy of the nucleon if we're being relativistic about it, as measured in its rest frame. The total measure energy of the nucleus would, of course, be the sum of all the masses minus the mass defect, which is what we also call the binding energy. The second thing is that the nuclear force is short-ranged. And when I say short-ranged here, it's the same definition that Professor Kaplan was using. It means that after some distance, it goes to zero. This is, of course, is in contrast to Coulomb or gravity. How do we know this? We know this because as you add more particles to the system, the size grows in a predictable way. if you call the mass number of the nucleus capital A, then the radius of a nucleus is approximately 1.2 Fermis times 10 to the 1/3. Again, a typical nucleus. I'll actually talk about cases in which this is violated later, but for now, let's think about a generic nucleus, something nice and stable, maybe iron, typical stable isotope of iron, and both of these things would be true. So this means, if you just think of it semi-classically, right, that each nucleon occupies a volume of about this 1.2 Fermis cubed of order, let's say. All right, so that means if we take this number 2 and we turn it into a typical momentum for the particles in the nucleus, we can do this by dividing P by computing the de Broglie wavelength of the corresponding nucleus is going to be about, corresponding particle is going to be at 1.2 Fermis. We can turn this into a momentum using the Broglie relation, and we get, sorry, not 200 Fermis, 200 MeV, about. Maybe a little bit less, but not much. Now, 1 and 3 together, where it means that we can understand the nucleus quite well using non-relativistic descriptions, at least in terms of kinematics. There will be extreme cases. So for instance, if we think about extremely dense nuclear matter, we might want to start worrying about relativistic effects. But generically, the nucleus is quite non-relativistic in terms of its kinematics. But I want to remind you that one of the main reasons that people are interested in nuclear physics is because the conversion of mass into energy, as I already alluded to, is key to nuclear physics's technological usefulness. So if we think about this, the ability to change the amount of mass in the particles on the left-hand side and the right-hand side of a nuclear reaction is exactly what leads to the release of energy. So if we think about something like this, which is what people are pursuing for fusion at nuclear reactors, then the particles on the left-hand side of this reaction have more mass than the particles on the right-hand side, and the mass difference gets released as kinetic energy of these things, which we can turn into heat. Now, why should that make you interested as particle physicists / quantum field theorists? I think it makes it interesting for 2 reasons. The first reason is that when we say that we're going to do non-relativistic EFT, we still have to worry about these mass changing effects. And the second one is that coupled channels effects are happening all over nuclear physics. So for instance, in this case, you have to think simultaneously about the elastic scattering process and the possibility that you will release energy through this other channel that is below the threshold for this reaction. So coupled channels effects are everywhere. So Professor Kaplan already alluded to one of these in his lecture. So even in the simple case of neutron-proton scattering at low energy, this channel is coupled to the capture, the fact that these 2 particles can capture on one another and form the bound state of the deuteron, and in doing so, in order to conserve mass and energy, they have to emit a photon. So you'll hear people call this NP to D gamma. But this is if you want to think about it this way, you can think about these as 2 channels that are open if you come in the neutron-proton channel. Now, what is this D thing here? This deuteron is actually, I'll denote it this way, a bound state of a neutron and a proton. The deuteron is bound by 2.225 MeV. So what does that mean? That means which, as Professor Kaplan pointed out, is kind of a small number compared to any scale that you're used to thinking about for hadrons. And so this indeed becomes the reason I went through this here was to exactly so we could talk about the scales of nuclear physics. And apropos of Professor Kaplan's point that effective field theory is not some monolithic thing that you construct once and for all and are done with, but instead is a technique for attacking the physics of systems with a separation of scales, I want to call out for you the fact that there are actually many different effective field theories of nuclear physics depending on what nuclear physics you want to describe. So let's talk a little bit about, now, I have to say at this point that I would have been happier to do this next thing using a slide because you will soon discover that my artistic ability is, or lack thereof, is exactly what drove me into theoretical physics. Okay. So the key letter in this subsection title is EFTs, plural, for nuclear physics. So anytime we construct an effective field theory, we need to think about the relevant energy / momentum / distance scales. And from that, we need to make some postulates about what the active degrees of freedom are. So we're going to discuss the active degrees of freedom, which I'll write DOF, which means let's talk about scales. Okay, so up here at a scale that maybe you're all comfortable with working at of about a GeV, I don't know, maybe that's already a low energy scale for you. I saw that the title of this week is, what is it, from low energy to ultra low energy, which I'm sure my condensed matter friends would find very amusing, that MEV scales are low energy, but just serves to make the point that everybody's low energy is someone else's high energy. So maybe you're comfortable thinking about physics at a scale of a GeV. This is maybe the last time that you'll see this scale in my lectures. And up here, as far as I'm concerned, if we want to do nuclear physics up here, we're stuck doing lattice QCD. I shouldn't say stuck. What I mean by stuck is that here the problem is sufficiently complicated and there are sufficiently many different active degrees of freedom that, as Professor Kaplan pointed out, effective field theory is not a tool that, or at least no one has figured out how to systematically apply effective field theory to this problem. So here we have mesons with, gluons and QQ bar pairs inside them and all sorts of complicated non-perturbative dynamics. We have baryons, which don't just have 3 valence quarks. Oh, that's what I was going to do. I saw the color chalk and I was excited. Okay, there we go. We have 3 valence quarks. Just so you can say that I actually talked about QCD, I'll give each of these a different color. Okay, and they're exchanging gluons, and I'm not going to go the full distance and do like the, the gluons in the octet, right? But fine, but in principle, they're exchanging gluons. And then there's some complicated C stuff going on, which gives the nucleon the bulk of its mass. Fine, there's all that stuff, right? But nuclear physics happens at a significantly lower scale. A lot of traditionally nuclear physicists have liked to think in terms of pion exchange. So I'm going to actually make this axis more or less logarithmic. So if we come down by an order of magnitude, we have the pion, whose mass is 139 MeV if it's charged and 135 MeV if it's neutral. And the effective field theory that Professor Isidori is going to talk about is chiral perturbation theory. I think Professor Kaplan's going to do an introduction to that soon. So in this effective field theory, this is a low energy scale, and these are the high energy scales. And in this effective field theory, all of this stuff is integrated out, and the active degrees of freedom are pions. So in nuclear physics context, you could be exchanging them between nucleons, or at this stage, you could also be considering the effects that they have on nucleon structure. So the fact that presumably there are so-called pion clouds around the nucleons. If you are, now an important distinction here that I haven't yet made on the y-axis is that in a non-relativistic EFT, which I've argued is what we're going to be doing, you have to actually be quite careful about whether you're talking about the energy scale or the momentum scale, right? So Professor Kaplan already pointed out that here we're going to have this kind of relation. So in relativistic EFT, someone tells you that they're going to integrate out degrees of freedom with energy of 1 GeV, and because it's relativistic, they might mean momentum, and you don't care because the energy is of order the momentum. But in a non-relativistic EFT, it actually matters whether we're going to integrate out, like whether we're talking about momentum scale or energy scale, because they're very different. So for instance, an energy scale of 8 MeV, as you already saw over here, corresponds to a momentum scale, an energy scale of 8 MeV turns out to correspond to a momentum scale of 200 MeV, which works out about right if you do the p squared over 2m. So here, in this case, if we integrate out energies of order m pi, because we argue that we're interested in momenta of order 200 to 300 MeV, and so we are no longer, but we don't consider pions as degrees of freedom that can be produced in nuclear physics, because most of the time in nuclear physics, we don't have pion production going on. Then we get something which is generically called chiral effective field theory, in which we've integrated out the pions that can go on shell, and we're left solely with pions that generate potentials. So I think this may be something that Dr. Mohapatra is going to talk more about, right? This distinction between the exchanges that generate potentials and the exchanges that can produce physical on-shell particles. So this is chiral effective field theory, and by doing systematic corrections to this one pion exchange, you can get a whole bunch of different potentials, cross diagrams, higher order couplings, and chiral perturbation theory come in, et cetera, et cetera. And this is the foundation for a lot of activity in so-called ab initio nuclear physics, which takes the potentials you derive this way and then solves for the structure of nuclei. But I'm going to go even further down in energy scale. If we go down to tens of MeV, and if you work out the binding momentum, like so if you take that 2.225 MeV, you stick it into the square root of 2 times the mass of the nucleon, you get about 45 MeV of binding momentum. And this is what I'm going to call, this is the binding in what I would call halo nuclei. So these are nuclei whose typical momentum is significantly lower than the generic nucleus I was talking about over there. So the picture here is of a nucleus. So here I have some complicated nucleus where all sorts of stuff is going on. Maybe this is the alpha particle. And then I have maybe a neutron and a proton. It's actually a pretty good picture for helium-6, which where the helium-6 is bound by 1 MeV, which is small compared to the binding of the alpha particle, which is 28 MeV. So down here, we're going to use a completely different EFT called halo EFT or short-range EFT. And these are really just children of the pionless EFT that Professor Kaplan introduced in his second lecture. But we're not done. everybody's high energy is someone else's low energy. Sorry, other way around. Everybody, yeah, no, that's right. So I guess either one is true. So if you go even further down, this is not something I'll talk about, but I think it's important to use it as an example of this principle. If we go further down to hundreds of keV to 1 MeV, then you can actually think about the amount of energy you need to take a deformed nucleus and excite it in rotational modes or vibrational modes. So these sort of very old school types of nuclear physics excitation can be formulated in a very lovely way as an effective field theory, complete with aspects like symmetry breaking and nonlinear realizations of the symmetry, so on and so forth. But the energy scale is now down here, and all this stuff, which for people doing, say, chiral effective field theory is a low energy scale. If you're interested in rotations of nuclei, rotations of, plutonium that take only 10 keV to excite, then 100 MeV for you is a very high energy scale, and you don't care a fig about the pion. Okay? So where are we going to live today? Yeah. Chiral EFT, the degree, it's a very interesting question, right? So the degrees of freedom, the degrees of freedom that can go on shell and reach the detector are neutrons and protons, but they interact via instantaneous potentials, which are due to the exchange of pions. So it's not chiral perturbation theory for two reasons. The first reason is what I just said, right? That the pions have been, let's say, so again, Dr. Mohapatra is the expert on this, but you integrate out what are called the radiation pions, and you leave yourself solely with pions that generate potentials. And the second reason is that it's not perturbative. So now we're going to come to a very important fact about nuclear physics, which I think is underappreciated by particle physicists, if I may be allowed to say so, that nuclear physics is intrinsically non-perturbative. If that wasn't true, none of us would be here, because there would be no nuclei and we would not exist. All right. So nuclear physics is intrinsically non-perturbative. So chiral perturbation theory cannot work for nuclear physics, not as written down, because it's a perturbative expansion of the amplitude. You're going to have to do something to make it a chiral effective field theory in which there is some non-perturbative piece. So yeah, so in Chi-P, so to make this step here, you notice that this pion went away. So what you do is you integrate out the effects of the pion on, for example, nucleon structure, and you put those into higher derivative operators, or they become higher order effects. And at leading order, what you have are structureless nucleons interacting via potentials that are generated by the exchange of a pion. All right, so as Dr. Mohapatra will say, this is the same thing you would do if you wanted to describe positronium. At leading order, you wouldn't do all the QED stuff. At leading order, you would just do E plus, E minus in a non-relativistic bound state interacting via the Coulomb potential. And then all those other things would be higher order corrections to that, okay? This one here or this one here? This one. Okay, so this is depending on who you ask, this is a leading order effect, and this is some higher order effect. I didn't say there was no perturbation expansion, right? I just said that the problem is intrinsically non-perturbative. So you're going to need to find some piece and declare that as leading order. Yeah, and indeed there's a now, like, I don't know what it is. What is it? It's like 20, 28-year discussion about whether this should be treated non-perturbatively or not. Okay, right. So, yes. And indeed, the scale matters here. So my answer to this question, and I don't think we're going to get to that this week, so I'll just tell you my answer now. My answer would be that if you're interested in physics at momenta of order a few hundred MeV, then you have to treat this non-perturbatively. But if you're interested in physics at a lower momentum scale, it becomes a perturbative correction to the theory that that Professor Kaplan already introduced and I'm going to tell you more about. So again, it's scale dependent, right? Whether that's strong or not basically depends on how close the two nucleons are to each other. But it's clear that so it's going to be some sort of Yukawa type interaction. So how strong it is, it matters what distance scale you're talking about. All right. So let's see, how much more? Okay, I got a little bit, so I can finish part one, section one of my lectures over here. So here are some observations. Most of these we've already covered, but I'll write them down for summary's sake. Number one, we need only nucleons, not antinucleons. We're nowhere near touching the 2 GeV free energy you'd need to produce an NN bar pair. Number two, nuclear physics is non-perturbative. Which, like if I write NP, that means it sounds like it's a particular class of computational problem that's difficult to solve, which is not actually so untrue. So you need a reason to go beyond tree level, at least. But you don't want to solve, this is exactly this conversation I was just having with, I'm sorry, what is your name? Atun? Atunu? Okay, yes, with Atunu. But you don't want to have to solve everything everywhere all at once. So you need a M0, some sort of leading order thing. I will try and call it A, so I'm consistent with Dr. Kaplan's notation. And then an organization. And of course, given that this is a school on effective field theories, I will argue that effective field theories are the organization you want. I'm not supposed to write over there, right? Okay, so I will do we'll cheat. You're going to have to read from right to left for a minute. And then number three, you need a scale separation. Or eventually, we're going to want to talk about Coulomb. Because if you ask, so here's an interesting question for you. So, let's think about the isotopes of, I don't know, beryllium. Okay, so beryllium has atomic number 4, and there's a bunch of different isotopes. Beryllium 7 is radioactive, it's unstable. Beryllium 8 is not quite bound, and then beryllium 9, beryllium 10, beryllium 11, beryllium 12, up to I think beryllium 16 now. But then it stops. So what is it that determines which ones are stable and which ones aren't? So on the proton-rich side, it's this. It's that if you get, so why is, beryllium 4 not stable? Because you can't bind 4 protons together by the nuclear force because the Coulomb force stops you. And then beryllium 5, the neutron doesn't give you enough additional attraction. Beryllium 6 is almost bound. Beryllium 7 is the first system for which the bound state has an energy less than the constituents, the first system for which the mass defect is a positive quantity. and then so on and so forth. And then what stops you on the other side is the Pauli principle. So you just can't keep putting neutrons in the nucleus forever because they're fermions, and you have to keep putting them, if you like, further and further out, and then you, in the end, you run up against the problem that you can't keep putting them further and further out because the nuclear force is short-ranged. All of which is to say, no effective field theory for nuclear physics worth its name can happen unless we also think about the fact that nuclei involve Coulomb. We have to talk about Coulomb eventually because of protons and their repulsion, and that's important for nuclear stability. And then, where did I put my list? I put it down. Okay. Is that the end of, okay. Yes, there we go. And, yes. And then, why do we do all this? We do all this because, as Professor Kaplan said, we don't just fit the parameters of our effective field theory to processes involving strong interactions and walk away. Effective field theory will allow us to couple the electromagnetic and weak force. And when we do that, we're going to do this in a way that respects ward identities and accounts for all operators. So maybe you know that in QED, there's no gauge principle that stops you writing down an interaction that would give the electron a magnetic moment. So in QED, I could write down operators like this. This is not forbidden by the QED gauge symmetry, right? But this operator is an irrelevant operator. If I use the relativistic counting of fields, this has dimension 3/2. This thing has dimension 2. This thing has dimension 3/2. So this is a dimension 5 operator, which is why it isn't typically included when people write down QED. Now, experimentally, we have no evidence. Is this true? I guess I can say that, right? So given that the G-2 anomaly of the muon has been declared to not be an anomaly because we trust lattice QCD more than we trust experiment, we have no evidence for this kind of operator for leptons, but we have this operator all over the place for baryons because they, the so-called anomalous magnetic moments of the proton and the neutron need this operator to carry them. So we're going to, so in the nuclear effective field theory, because we're going to write down all operators consistent with the symmetries, we're going to get this kind of operator for electromagnetic processes and all sorts of other interesting operators that encode in some sort of multipole expansion the electromagnetic structure of the nucleons. Okay. So that is the end of section 1. So what am I? Okay. So let's go on to section 2. And much of this will be very familiar to you because section 2 is basically a recap of Professor Kaplan's discussion of the short range or pionless effective field theory. Does anyone have any questions while I erase this lovely large blackboard? I'm not sure I ever lectured on a blackboard that was this wide before. It's kind of a physical, and you notice how I started writing very generously and then I got more and more cramped as I got to the right-hand side of the board. No questions? Okay. All right. So this effective field theory is, we're going to start, let me get my colored chalk again. I'm going to get my steps in this way. Okay. All right, so we're going to start here. Somewhere in the middle of all the scales, Why are we starting here? Because this is the simplest nuclear EFT that I know. Please, yes. Are you asking if it's large enough for a decent scale separation? Yeah, so, I mean, actually, that's by no means the worst scale separation on this list, but yeah. So that's actually a problem with a lot of these nuclear EFTs, is that the scale separation, the expansion, the EFT expansion is sort of in powers of something like a half or a third. So this is not BSM physics. It's not even Chi-PT in the meson sector, right? You have to do several orders before you can convince yourself that this is actually a useful expansion. Fortunately, a lot of the EFTs are simple enough that you can do several orders. The fact that they're non-relativistic helps because the proliferation of diagrams is not terrible. Yeah, so that is a very interesting question, right? So people who are doing this are trying to, let's say, understand rotations and vibrations of nuclei as some sort of emergent phenomenon. So you could hope that if you do this accurately enough, you can get the rotations and vibrations accurately enough that you can describe the very low energy part of the spectrum. But my answer to this is actually that it might be more efficient to split the problem up and essentially match across the scales. So, yeah. Yeah, so you would use something like, so I actually work some on capture reactions for astrophysics. And I would say if you're doing them at like tens of MeV, you're going to do something like this. And then if you're doing them at 1 to 2 MeV, maybe you do something more like the halo EFT / pionless EFT that I'm going to talk about. All right, so to repeat what Dr. Kaplan already wrote down, so this is a non-relativistic effective field theory. This is the nucleon mass. This is the simplest operator, which is irrelevant, even in the non-relativistic theory, but as Professor Kaplan said, can be tuned if you're interested in describing physics near a shallow bound state. And I'm interested in describing physics near a shallow bound state because that big green circle I drew is a circle around a whole bunch of bound state systems that are bound by much less than the natural scale of the problem. The natural scale of nuclear physics binding is 8 MeV. These are nuclei that are bound by 1 to 2 MeV or less. Boron 8 is bound by 137 keV. There's a resonance in oxygen 26 at like 25 keV. So there are a bunch of states in nuclear physics that exist very near the threshold and whose binding is much less than the typical binding of nuclear physics. Okay, so I said the next part. All right, now I'm going to do a little bit of a comment. So this came up towards the end of David's lecture. So in principle, this nucleon field I'm writing down has 4 components. Does anyone want to take a stab at what the 4 components are? So they're fermions, right? So spin up and spin down. So then why am I saying there are 4? Isospin, very good, right? So I have proton spin up, proton spin down, neutron spin up, neutron spin down. So if I actually wrote this down and I meant it to be a 4-component theory, then a fun thing about this is that this Lagrangian is actually SU4 symmetric. This is actually a very old symmetry in terms of people thinking about nuclear physics. Wigner wrote a couple of wonderful papers about SU4 symmetry in nuclei and how it impacted nuclear structure and nuclear beta decays in 1936 and 1937. So we're not going to go all the way to the SU4 limit, but we will go to the isospin limit, in which case the proton and the neutron are just different states of the same particle, and we have isospin symmetry. So NN channels can be then labeled by their total spin and isospin. We're going to do this interaction here. I don't see any angular dependence in it, right? As Professor Kaplan said, it's going to produce some delta function. Delta function is intrinsically S wave because it's the same, it's spherically symmetric. So we want to think about S waves. But then I have to be a little bit careful because nucleons are fermions. So what do we know about fermions? The total wave function has to be antisymmetric. So if I build a wave function with spin 1, is that antisymmetric or symmetric? Right, this one is symmetric because, for instance, 2 spin-up particles, which I can just do this, right? This is part of this multiplet. So this has to be a symmetric multiplet. So then that means that for S-wave nucleons, you can only have spin 1 if you also have total isospin 0, so that you can make the total wave function antisymmetric. And similarly, if you say you want to think about neutrons and protons with opposite spin, so with this wave function, then you can have t equals 1. So this was this. So here in this channel, which nuclear physicists denote the singlet S0. So here that's because this is the L equals 0 part. This is the spin, and this is the J. Since L equals 0 and S equals 0, J has to be 0. So here in this state, we can be thinking about proton-proton scattering, proton-neutron scattering, or neutron-neutron scattering, whereas in this state, the only possibility is neutron-proton. And this channel here with isospin 0, this is the one where a bound state exists, and this is the one where there's a virtual bound state, meaning that you have a very large negative scattering length. So if I remember the numbers correctly, the scattering length here is 5.4 Fermis, and the scattering length here is minus 23. Well, that's I don't remember. I'll just put minus 23, point something Fermis. But this is actually for neutron-proton, because that's the one we can do where we're not obscured by Coulomb. If you do it for proton-proton, you have to come up with some definition of what you mean by the Coulomb-free scattering length, because you've assumed isospin, and doing it for neutrons is hard. All right, so let's see. All right, so to repeat the Feynman rules from Professor Kaplan's lecture, if I have a line for one of these nucleons carrying 0th component P0 and 3 momentum P, then this will be the propagator. This interaction generates a vertex like that. And so if I compute the amplitude at tree level, I just get minus C. So if I do I times A at tree level, I get minus IC. So that would mean A is minus C. Dr. Kaplan already took you through the calculation at one loop. So that's this diagram is tree level. One loop looks like this. So here for the one loop, we get minus c squared times integral, where capital D here is the number of spatial dimensions, because I've done the integral over P0 using the residue theorem. And in doing so, I've obtained the non-relativistic propagator for two particles with reduced mass m/2. Fun fact, if you do this, I mean, not surprising, but if you go through this calculation and you put two different kinds of particle in your theory with two different masses, as you might want to do, for instance, if you're interested in a beryllium-10 nucleus with a neutron orbiting it, then it's this, what comes out here is 2 times the reduced mass. It's actually kind of a fun. Did you ever think about the fact, here we go, that the reduced mass is the harmonic mean of the two masses involved? This is actually exactly because of the way inverses add. So 1 over mr is 1 over m1 plus 1 over m2, because you add the inverses when you do this calculation. Okay. So now we have to do this integral. So during the, what is that, the 5th hour today? The 5th hour today, because by then you will be getting tired of hearing people talk to you, we will have you work out this calculation using dimensional regularization. I'll give you some steps to do it, but if you work out this, so let me tell you what the first step here. The first step is actually, I would argue, not to do it for positive energies, but to do it for negative energies and then analytically continue. And in fact, if you want to think about bound states, you want it for negative energies. So if I think about this for some energy minus B, where B is greater than 0, then this becomes c squared integral ddp over 2 pi to the d1 over b plus d squared over m. Sort of like, oh, okay, that's kind of interesting, because probably you know how to do integrals like this. Where mb is actually the square of the momentum associated with the binding energy B. So I'm going to, for the moment, just claim without proof, and or by referring to what Dr. Kaplan wrote down towards the end of his lecture, that if you do this integral in dim reg, you get this. But then, as Dr. Kaplan was saying right at the end of his lecture, this thing has a funny feature, which is that you've started off with an integral that you darn well know is divergent in d equals 3. You've done it using dimensional regularization, and you get a completely finite answer. Right? So just follow along with me here. If I put d equals 3, just into this formula, I get mc squared over 4 pi to the 3/2. I get gamma of -1/2, which is finite, right? And then I get 1 power of this gamma scale. This is -2 root pi. And so I get minus mc squared. This cancels one of these. I get a 4 pi, and I get gamma. So I think tomorrow, Dr. Kaplan is going to point out that you don't have, that we've smuggled in a particular subtraction scheme here. In particular, when we did this, we've said we did this with no subtractions. Sorry, no, yeah, we did this with no subtractions. We didn't have to remove any 1 over epsilon poles because we didn't see any 1 over epsilon poles. So here, minimal subtraction means no subtractions, but that's a choice. And you're going to see tomorrow that in this problem, a more natural choice would actually be to subtract the pole in d equals 2 before you analytically continue to d equals 3. So this caused a lot of, I mean, by the way, this whole like, oh, how did this go from being infinite to finite? This caused a lot of people who were used to doing field theory some heartburn. And what you realize if you sit there and look at all the steps along the way is that this formula that goes from here to here is strictly speaking only valid if d is larger than 2. So, because of course, right, you can only write this in terms of gamma functions if this thing is finite. And then when we do dim reg with minimal subtraction, we just analytically continue it to places where it's not true, and we just drop all the extra bits, which is how you get rid of all the power law divergences in dim reg with minimal subtraction. And in most problems, that's a feature, not a bug, because you don't want to keep the power law divergences because then you're going to have an extra scale, and this is going to produce problems with gauge symmetry and blah, 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 blah. But if you have a fine-tuned problem, throwing away at least that linear divergence is a bug, not a feature, because it means that you lose track of exactly the physics that makes this bound state shallow. You lose track of the fine-tuning between the attraction coming from the interaction C and the virtual fluctuations that go like 1 over p squared. All right. But I'm not going to fix that problem today. I'm just going to plow blindly ahead because you can do this calculation in minimal subtraction. It's just that there are some things that are puzzling when you're done that are less puzzling if you use a more natural subtraction scheme for this problem. Okay, so if I analytically continue back to positive energy, I get a one loop A that's mc squared over 4 pi times the square root of minus me minus I epsilon, because I continue B to E plus I epsilon. So here, when I take the square root of the negative number, because I'm at minus I epsilon, I'm obligated to go to the negative imaginary axis, not the positive imaginary axis. And so I get the minus sign that Professor Kaplan wrote down. And then I can go through the matching as Professor Kaplan did, right? So now I have, if I match to the threshold amplitude, I discover that C is indeed 4 pi A over M. And then this one loop expression gives me the one loop correction. So if I do the matching, I get that C is 4 pi A divided by M. And then the one loop is going to be minus I times 4 pi A squared times K over M. And today you're going to do an infinite loop calculation in the next 2 minutes. I know that that's all we have because it's almost lunchtime, but it's fine. We're going to do infinitely many loops in 2 minutes. If you write down the 2-loop amplitude, well, what does it look like first? It's this interaction times 2 of these bubbles. But because this thing is a contact interaction, these bubbles factorize. Right? There is no communication of the momentum that's flowing around this bubble to the momentum that's flowing around this bubble. So it's exactly the same integral every time. So if you sit down and apply the Feynman rules for this case, you just get minus I, actually I'll write down, yeah, minus I times C cubed times the integral that we already did, squared. And if you plug in the results that we already derived, you discover that this is 4 pi over M times minus IAK squared. So now, as already claimed in the previous lecture, what you're seeing is times A, is that this is an expansion in powers of A times K. So tree level is A, One loop is A times K suppressed, two loops is A times K squared suppressed. And this pattern will continue. So if you did this at n loops, you would just get this. So this is a series that we can all sum. Yep, I got it. My son is in 10th grade and he has been learning about geometric series. I'm very happy because many of my papers revolve around resumming a geometric series. So this is not I times A, this is A, sorry. So if we do A, all the loops, we get 4 pi A divided by M, 1 minus IAK minus A squared K squared plus blah, 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 which is 4 pi A over M times 1 over 1 plus IAK, which is and so that is how you derive that leading order amplitude that Professor Kaplan was working with using the minimal subtraction scheme. All right, so yeah, the thing is flashing red at me. It is angry. All right, so two comments. The first comment is I needed to sum to all orders to get this. So this does fulfill my demand that there be some part of the problem that is non-perturbative. Here, the part of the problem that's non-perturbative is this leading order coefficient. But as I already said, the way that this resummation happens doesn't really match the physics of the non-relativistic shallow bound state because nowhere do I see, I have just shoved all my balance between repulsion and attraction into my renormalized coupling 4 pi A over M. And then I've just done resummed that thing at leading order. And in particular, this leads to problems like, should I really be doing this if, what happens if A goes to infinity? What does this mean to do this if A goes to infinity? Because then each order in this expansion is actually bigger than the previous one. So, all right, that's why you might want a different subtraction scheme. So with that, I will take questions, but I also believe it is lunchtime, so you should bear in mind, I'm happy to answer questions during lunch. I'm also coming back after lunch, so however we want to do it. All right, thanks for your attention.